Hi everyone, I'm Rinil Delino from the Mathematics Department, and today I will discuss with you the antiderivative and the power formula. So for this lesson, we will cover the following topics. First, we will discuss the definition of antiderivative. Next, we have the properties of indefinite integrals, or called as the basic integration formulas. Next, we have the integration using power formula. And the last is the integration using u-substitution. So before we start, now let me discuss with you the objectives of the study. So at the end of the lesson, the student must be able to define anti-differentiation or integration. Be familiar with the properties of indefinite integrals. Perform basic integration by applying the power formula, and perform integration using simple substitution of antiderivative. Let me start by defining what an antiderivative is. So by definition, a function big F is called an antiderivative or integral of the function small f on a given interval if the first derivative of the function big F of x equals the function small f of x for every value of x in the interval. Like for example, the function big F of x equals 1/4 x to the fourth is said to be an antiderivative of the function small f of x equals x cubed on the interval negative infinity to positive infinity, since for each x in the given interval, the first derivative of the function big F of x equals the derivative of 1/4 x to the fourth with respect to x, which is equal to x cubed. And this function is also the same as the function small f of x. However, the function big F of x, which is equal to 1/4 x to the fourth, is not the only antiderivative of the function small f on the given interval. Because if we add any constant c to 1/4 x to the fourth, the function denoted by g prime of x equals the derivative of 1/4 x to the fourth plus c with respect to x equals x cubed, which is also the same as small f of x. So in general, once any single antiderivative is known, the other antiderivatives can be obtained by adding constants to the known derivatives. Thus, this function 1/4 x to the fourth, 1/4 x to the fourth plus 3, 1/4 x to the fourth plus 5, and so on and so forth, all of these are antiderivatives of the function small f of x equals x cubed. So in general, according to this theorem, if the function big F of x is an antiderivative of the function small f of x on an open interval, then for any constant c, the function big F of x plus c is also an antiderivative on that interval. So moreover, each antiderivative of the function small f of x on the interval can be expressed in the form of big F of x plus c by choosing the constant c appropriately. The process of finding antiderivatives is called antidifferentiation or integration. Thus, the derivative of big F of x with respect to x equals small f of x. Then integrating or antidifferentiating the function f of x produces an antiderivative of the form big F of x plus the constant c. So to emphasize this process, we use the following notation. The integral of small f of x dx equals the function big F of x plus the constant c, where the quantities on the left side, the integral of f of x dx, is called the antiderivative. This symbol is called the integral sign. F of x is the integrand, c is the constant of integration, and dx indicates that x is the variable of integration. Some of the properties of indefinite integral and basic integration formulas are listed below. So these properties need no proof from the fact that these properties are also known properties of differentiation. The first formula is the integral of dx equals x plus c. So this is obtained from the definition of indefinite integral. Then number 2 is the integral of the product of the constant c and the function f of x times dx. Because c is constant, so we factor this out. So we have c times the integral of f of x dx. But from the definition of the definite integral, the integral of f of x dx is f of x, big F of x, plus the constant c, times the constant c, so you have c times the function big F of x plus the constant c. Okay, the third formula is the integral of the sum or difference of n functions with respect to x. So this is equal to the sum or difference of the integral of each function. So given the n functions, f sub 1 up to f sub n, and then the integral of the sum or difference of these n functions is obtained by applying the distributive property. You distribute the integral sign together with dx to each of the term. So therefore, the integral of f sub 1 of x plus or minus f sub 2 of x plus or minus and so on and so forth plus or minus f sub n of x dx is equal to the integral of f sub 1 of x dx plus or minus the integral of f sub 2 of x dx plus or minus and so on and so forth plus or minus the integral of f sub n of x dx. Okay, the fourth formula is called the power formula. And the power formula is of the form integral of x to the n dx. And this is equal to x to the n plus 1 over n plus 1 plus the constant c, provided that the value of n is not equal to negative 1. So you can easily apply this by increasing the exponent by 1. So you have x raised to n plus 1 divided by n plus 1 plus the constant c. The last topic for this lesson is the u-substitution. This is also called the general power formula. In evaluating the integral of f of g of x times g prime of x dx, it will be more convenient to let u be g of x and write the differential form du equals g prime of x dx. So this integral by substitution can now be written as f of g of x, where g of x is u, so you have f of u times g prime of x dx, which is du. So we have the integral of f of u du equals the function big F of u plus the constant c. So from this equation, we can generalize the power formula as follows. We have the integral of quantity f of u, quantity raised to the n power, times the differential of the function f of u. And this is equal to the function, which is f of u, quantity, close quantity raised to the n plus 1 over n plus 1 plus the constant c, provided that n is not equal to negative 1. Or, if we let f of u as u, you have u to the n, and the differential of f of u as du. So we have u to the n plus 1 over n plus 1 plus the constant c, provided that n is not equal to negative 1. The method of u-substitution may be applied in evaluating an integral with the substitution u equals g of x and du equals g prime of x dx. So in summary, we have learned that the indefinite integral of a function is not unique, as it includes the constant of integration denoted by c, which can be an arbitrary number. Okay, you also learned how to apply the basic formulas and the u-substitution. Many times, now we have to rewrite the integrand to match it in standard form.